Hi there, good morning and welcome to the Mentor Hot Seat Interviews. I'm here with Joe Sawicki, who's Vice President and General Manager of the Design to Silicon division of Mentor Graphics. And we're going to talk about a number of the nanometer issues that are coming up and what Joe's view is on the future and how things will pan out over the next few years. Okay, Joe, I'd like to look at the first question, which is, what do you see as the new challenges coming up at 28 nanometer, 20, 14, that require innovations to be made in the design to silicon space?
That's a great question, Chris. I mean, if you look at it, one of the bigger stories that's been occurring fairly consistently now for a number of years is with delays in EUV, is that having to continue to stretch optical lithography over this period of time has been incredibly challenging on the manufacturing side. And so what that requires us to come up with is brand new sets of tools all focused on getting a reasonable pattern against what the designer is trying to put onto the chip to deliver functionality. Probably the biggest thing that's occurred at 20 nanometers is the introduction of double patterning. Essentially, if you want to go below an 80 nanometer half pitch, which you want to for density requirements, you need to do that with double patterning. And it's a trivial thing when you think about it. You know, when you used to doodle and do a little cross in one box and a little different in the other, the whole thing with double patterning is on a billion shapes. You have to make sure that none of those touch each other that look the same. And that's interesting work to do. And so we've been working on the manufacturing side for about probably 3 years now on that, and that's well in place. And now, because we did that work, we're also integrating those tools now up in the design space so that you can tell the designers, what are you doing, what can you possibly change about the design so that you can get that patterning, get the density that you need, and do that at 20 nanometers.
Yeah. I mean, what do you see as the prognosis for EUV? Will we see it coming in the near future, and how far is double patterning or even triple patterning going to push 193 nanometer?
Yeah, it's an interesting question. I mean, I can look out and see a future where you can pattern down to a single-digit node with optical lithography. You will have to go from double to triple patterning. We'll probably start doing sidewall type stuff, but you can get it done. Yep. EUV, with its ability to do that potentially with one mask layer, faster processing, less etch, offers potential for being cheaper. I just don't know in terms of the when that's going to be available, if that's going to be available. I know that people are spending an awful lot of money to make it happen. I do know that customers come at this with an almost willful optimism that they need it, so it has to happen. But we yet to see the evidence that it will happen.
Yes. Yeah. I mean, do you see double patterning being able to be pushed, a long way, or at least multiple patterning to be pushed?
From a technical perspective, absolutely. Yeah. There are concerns about costs, but I always like to remind people, remember at this point in time, if we looked at the charts from 4 years ago, this was supposed to be the $20 million mask set. That didn't happen. And it doesn't happen because when you get to the point where, okay, if we don't solve problems in this space, then we're going to not scale. There's an awful lot of money, energy, and attention, innovation that's focused on taking care of those issues. So from a technical perspective, we can push it significantly farther. You have to go to triple patterning. You may eventually have to do the quadruple patterning. But it's all a matter of then focusing not just on the technical aspects, but making sure you can do so in a cost-effective way.
Yes, yes. We're also seeing as an alternative method of scaling the move to 3D, and on the way to that we've got 2.5D. Is 2.5D there, or are there sticking points? Are there challenges ahead for the 2.5D technologies?
Yeah, well, what's interesting about this, when we look at the 2.5D, 3D silicon interposer, or doing real 3D stacking, we mostly, at least for the next 5 to 10 years, don't really see it as an alternative to scaling, but as an alternative to multi-process integration and or boards or package-in-package. Is it because you can then take potentially RF or memory or sensor and logic, integrate that together in a much smaller form factor, driving much smaller traces, requiring much smaller driver circuitry, you can get really cool characteristics in terms of density, power, functionality. Alternative to scaling, and potentially that might be out 5 years where you'll stack homogeneous logic. But right now it's some obvious stuff of sensor stuff. Wide I/O memory looks like it could be a major winner initially in data centers, just in terms of what that does for power characteristics. In terms of the EDA flow to enable the multi-process stuff, the integration, it's an evolutionary step. You need to be able to add things that allow you to do things like verify multi-technology matching and make sure you're going to actually have bump pads where you have landing pads on the interposer. You need to be able to add test things that let you test the known to get known good die, but then do the integration testing to validate that the two things together didn't make something happen. Those are, I don't want to call them easy because it's certainly takes years of development, but it's not a revolution. And so I think we're in reasonable shape there. Bigger challenge on the interposer is, and the TSV is, again, it's the cost. It's always cost. Data center, it's obvious. Mobile, probably the costs need to get down a little bit more before we'll see that there.
Yes. But you see it as moving forward quite quickly.
It is definitely, the hype is being matched by enough reality that this is an area that everyone should be paying deep attention to, because I think it allows you to do some really interesting things competitively for a chip designer.
Yes. I mean, and looking at other issues, I mean, test is always clearly a big one for designers. What do you see as the trends for design to test? I mean, is it something that we pulled into the IP flow and sort of integrated into the into the IP aspect of design, or is it sort of a full chip kind of thing?
Yeah, well, it's interesting. I mean, we've got a fairly major focus on test, and it's almost all targeted at the quality, reliability, and yield learning aspects of test. So it ranges from just on these large SoCs, doing test as a flat problem at the end of the chip, runtime, the amount of thing it takes to put that together, just nasty. And so we are putting together methodologies that allow people to do hierarchical test and test reuse. We're putting together things that allow people to do a really cool thing where, okay, you get test failures. What did it mean? We have tools that allow you to do diagnostics and statistical information that's allowing people to find what are systematic yield issues in the foundry process that are affecting their design yield. And so that stuff's cool. Things like 1687 to allow instrumented test, particularly to align not just SoC but 3D. It's a rich area for innovation, particularly because if you go talk to most customers right now, they'll go, okay, the wafer scaling issues, okay, we'll see those look okay, the cost looks there, but the test cost issue could be a disaster.
Yes.
Or okay, my chip's cheaper, but it cost me $20 to test the thing.
Yeah.
And so we're spending a lot of energy there just to take care of those type of problems.
Yeah, and you see people sort of mining that data as well with the IP level. And
oh, absolutely, absolutely. I mean, we've had some fascinating cases recently. Like you would expect a 65 nanometer process. That's done, right? Yeah. There's nothing wrong with 65. Well, we just found a customer where we gave them the ability to grab about another 10, somewhere in the neighborhood, high single-digit, low 10% range of additional yield, because we found a particular problem that was occurring because of the way they were doing fill that was causing a slight collapse in one particular area of their chip, and it was causing them a yield problem at 65 by mining that very data.
Yes. Yeah, so it's not just the bleeding edge.
No,
it's happening all over the
yield ramp. You need it, but it's also it's an aspect of you do that at your mature processes. There's still going to be problems you're going to find.
Yeah. Okay. Sounds like there's a lot of interesting work ahead.
We have fun.
Yeah, that's great. So, okay, I'm Chris Edwards, editor with Tech Design Forum, and I've been talking to Joe Sawicki, VP and General Manager of the Design to Silicon division of Mental Graphics. Okay, thanks, Joe.
Chris, always a pleasure.
Good to see you.